Module 8, the universe to the atom, and we're all starting with the Big Bang. Um, so, the whole universe was in a hot, dense state till nearly 14 billion years ago. Expansion started. Now, the universe was so hot and so dense that the density of energy was able to convert into matter in the form of quarks, but these quarks were so hot that they would then disintegrate back into energy, or convert themselves back into energy. And this process happened continuously. The universe was in a state where energy and matter were almost the same thing, one turning into the other, turning into one again, turning into the other, constantly repeating. Expansion started. So the universe expands, and as it expands, it cools, right? Energy, when it turns into particles and antiparticles, which when they come back together again under the hot, dense state, they turn back into energy. However, if there's expansion, when energy turns into particle, antiparticle, if they expand, they're not going to come back together and they won't annihilate. We get to keep matter. Now, for some reason, more matter was created than antimatter. So after all the annihilations were done, we end up with a lot of matter, thankfully, because it's what I'm made of. The universe expanding allows quarks to be stable. They're no longer colliding with antiquarks. They're no longer converting themselves back into energy. Universe expands even more and cools down, like expansion of gas. The more you expand something, the colder you make it because the average temperature is dropping, because the energy is spread out. When you cool it down enough, quarks can condense with other quarks um, to form protons and neutrons, right? And a lot of other things, but those other things also break apart. It's really only protons and neutrons which are stable formations of quarks. Protons and neutrons, the universe cools down even more, and the neutrons decay into protons. Now, and single protons by themselves, that's a hydrogen nucleus. We've got hydrogen. This all took about 1 second of time. The universe is still billions of degrees hot and is now many, many, many billions of kilometers wide. Um, let's talk about some of the evidence. First of all, how do we know expansion happened, and how do we know roughly the time it took, the size it got to, and the temperature? Well, it's theoretical, but we've got good reasons. If the universe was expanding, if the universe wasn't expanding or was expanding too slowly, gravity would have pulled all the matter of the universe together and would have formed a black hole. And the universe currently is not a black hole, right? I can tell that for myself. If the universe was expanding too fast, then the quarks that formed wouldn't have been close enough to each other to condense into matter like we have today, into the protons and neutrons. We wouldn't have had any kind of complicated matter, which is good that it did. So we know we can work out the timings and the speed of all of this. We know that it can't have been too slow in expansion, black hole, or too fast, spread out quarks everywhere. Okay, but what was the evidence that made us think the universe had a beginning, started all in one place, condensed, um, and this 14 billion year ago number? So a guy named Edwin Hubble, he was studying galaxies, and he was trying to use the light of the galaxies to work out that the universe is expanding. So we have Earth, as usual, Earth in the middle, and he was studying the light from galaxies, and he was studying whether that light was redshifted or blue shifted. So there's one galaxy out there, it's called Andromeda, and Andromeda is moving towards us, and as it moves towards us, the waves of light shrink, they're squeezed together as it's moving towards us, and that makes it look more blue. However, out there are a lot of other galaxies, billions of them in fact, and every one of them that he looked at, they were all red shifted, meaning they're moving away from us, right? He saw that galaxies, there's our closest one, Andromeda, which is moving towards us, but for the most part, other galaxies are moving away from us, right? And so the normal idea is if you observe everything moving away from you, then you would imagine that their observing you are moving away from them, and the whole universe is moving away from each other. Everything's moving away from everywhere else. Um, Now, this is an okay observation, seeing that all the galaxies are moving away. That's good. That's showing expansion. But the real clincher was the fact that galaxies further away from us were moving away at a greater rate than the galaxies closer to us. So galaxies further away are moving away at a faster speed than the galaxies close to us. And this is really consistent. And a galaxy really far away is moving really fast. This is really consistent with the idea of an expanding universe. If you imagine a rubber sheet or a balloon that you're blowing up, it's expanding, and you think about 2 points on it. Now, if those 2 points are really close to each other, even when you blow up the balloon, you know, they don't get that much further apart. There's not that much rubber in between them to stretch them that far. But if two spots are on opposite sides of the balloon, even though the balloon starts in one place, when you blow the balloon up, they now move really far apart. So if this drawing here is the universe, right, and we imagine everything in one spot, it's like the balloon, um, and you have the Earth, and on the opposite side of the balloon universe, you have this galaxy over here, right? They start in one place, but as you blow up the balloon, they end up really far apart. However, the Earth and the galaxy right next to it, you know, the balloon, there isn't that much balloon rubber in order to stretch between them, right? The universe is expanding. There isn't much universe here to expand. There is a lot of universe here to expand. So we see faster rates of movement away for far away galaxies, slower rates of close ones. So not only do we know the universe is expanding, not only do we know that everything's moving apart, but we can see that the rate of expansion depends on how much universe is between us and them. So it seems like the whole fabric of the universe is what's expanding. Now, as we look out in the universe, we're actually looking back in time. The moon is about 1 light second away, 1.1 or something. So light from the moon takes 1 second for us to get to Earth. So when we see that light, we're seeing 1 second into the past. Light from the sun, about 8 minutes into the past. Light from the nearest star other than the sun, 4.2 years in the past. The further and further out we look, the more and more in the past we see. What happens if we look past all the stars, all the galaxies, and we look as far as we can into the universe? What do we see? We see the beginning, or at least very close to the beginning. We see the cosmic microwave background radiation. Let me find you a picture. Boom, beautiful. This is what we see, right? What this is, um, as stated, cosmic microwave background radiation. It's microwave, so we're seeing microwave light, and we're seeing it between the stars and galaxies at the edges of the universe. This is the light from the early universe, not too long after the Big Bang, only I think a few thousand years. It still is a long time. We got to the point where we said hydrogen existed, but it was still, that was 1 second after the Big Bang, we've got hydrogen. It's still billions of degrees, really, really hot. So that hydrogen is a plasma, which does not allow light to travel through the plasma, right? Any light that hits a plasma is absorbed by it because there's free charges. Universe keeps expanding, keeps cooling down. Eventually it cools down, so the plasma turns into hydrogen gas. The electrons and the protons in the plasma collide, and now it is see-through. Hydrogen gas is see-through, and all the light from the heat from the black body that was inside the universe is free to go. And this is the light that we can still see when we look 14 billion years in the past out at the edge of the universe. No matter where we look in any direction, we see this light. Um, we estimate that, like I said before, it's a few thousand years after the beginning of the Big Bang. Why is it microwaves? It's a, right, the M. It's it's black body radiation, and we'd imagine for something that's billions of degrees, or something like that, that we would have bigger wavelengths. So as the universe expands, even if the wavelengths were high intensity, as the universe expands, it pulls those wavelengths apart, stretching them out, and 14 billion years gives us microwaves. Okay, so cosmic, the space, microwave, because that's the length of the wavelengths, background radiation, because it's in the background behind the stars and the galaxies. Um, Okay, this is the evidence that led to the discovery of the expansion of the universe by Hubble. Since then, um, after Hubble's discoveries, scientists thought that over time, the gravity of the universe will pull all the galaxies towards us, and if enough time goes past, they'll go from redshifted to blue shifted, and eventually we'd get the opposite of a Big Bang, a nab-nib, where the whole universe crunches into one place. Enter scientist Brian Schmidt, um, a born in America, but I'm going to claim him is Australian now, lives here, and did his work here. And his work found that actually the rate of expansion of the universe is accelerating. It was expanding slowly at first, slowly. It's expanding faster and faster. In the future, if the rates continue, it should be expanding even faster. Um, Meaning that instead of the universe eventually crunching in on itself, it's just going to rip itself apart. That's the Big Bang.